And this is the title of my talk on the spin conversion phenomena in spintronics. And I'd like to just ask you whether you're familiar with the spintronics. Do you know the word spin current? If you know the word. So, but maybe then I'm going to repeat things. And I just decided to start very, very fundamental things. So then maybe all of you who know what spin current is, maybe get bored. But I'd like to just continue. Right. So this is a very important slide, which I have to show. I'm supposed to advertise the IEEE Magnetic Society. And this is a kind of one of the largest society in the world in terms of electric technology as a community. And there are 3,000 members, 300 student members, and also the other social society activity, the conference organization, and also one of these is this distinguished lecturers. Every year, 4 lecturers are selected, and they are giving lectures in relation to their specialty. So this year there are 4, and this are Alison Plateau, and Kami Fu, and also Mr. Inoue, and also myself. And I'm just talking about spintronics. So this is an important job which I have to do. So today I'd like to talk about this spin conversion, which is very versatile and very interesting. All these physical entities like heat, vibration, sound, light, and electricity, all these things can be interconverted via spin, namely spin currents and also spin accumulation, which I will explain to you later. So this is a very important scheme. And then this is the collaborators, and I'd like to just mention, today I'm going to talk topological insulator, Rashba interface, and also wireless metal, if I have enough time. And all these things is in collaboration with Professor Yoshitokura's group in Riken, and also this Professor Ishii's group in Kanazawa. He's a theorist, and we did the first principle calculation. And wireless metal, I collaborated with my colleague, Professor Nakatsuji's group in ISSP, University of Tokyo. And also, theoretically, this Alan McDonald and Fua Chen, at that time, the UTA, University of Texas Austin, they just helped us a lot to understand the behavior. These people are just my people in ISSP. Okay, this is outline. Start with the introduction, in which I'd like to explain a little bit about the spin currents, GMR, and also spin conversion, and then followed by the charge spin interconversion in surface and also interface states. And then I would like to just talk about this new material, which is recognized as wireless metal, this manganese-3 tin, and by using this, and we can see the very different type of spin Hall effect, which we call magnetic spin Hall effect. Okay, now introduction. Okay, let's begin with the spin currents. You may know what it is. In the spin current, and we're trying to benefit from the electrons, the degrees of freedom. If you look at Wikipedia, for example, and there is this kind of explanation. Electron carries elementary charge and also the spin. So which is rotating, spinning top, and which shows the spin angular momentum. Therefore, then you can regard this electron as an atomic size magnet. So this is very important. That's why we can benefit from 2 functionalities. So now then I'd like to just show you there are 2, charge and also spin currents. Charge currents, we know, which is very important for electronics. And spin currents, this is on the other hand, and very important for spintronics, which we are going to benefit from this spin angular momentum. Now, theoretically speaking, spin currents can be given by this simple formula, and which express velocity and spin-on, and also this spin density matrix. And then you sum up in terms of all the k vectors. And then you divide with the volume related, and then you get the spin current. But if you choose a particular axis for simplicity, and then you can deduce this simple equation, Js, that means spin current, is given by the upspin channel minus downspin channel. This is the basis of the current model. Now, more pedagogically, and if you look at the spin polarized current, which is realizing in the ferromagnetic material. When you pass a current in ferromagnet, let's say iron or cobalt or nickel, and then you can see different population of the up spins or down spins are flowing in one direction. So this is equivalent to flow of both charge and spins. By definition, total electric current is given by the sum of the two channels, up and down, which is non-zero in this way. Then the spin current, which is given by the difference, is also non-zero. This is what is happening inside ferromagnet, right? So experimentally, if we can realize pure spin current flowing like this. So up spin channel is from left to right, and down spin channel is opposite direction. In this case, you can see the charge current is well compensated. Therefore, as a result, you get flow of only spin angular momentum. This is what I mean, this pure spin current. Therefore, you just can expect. If there is no relaxation, then you can say this is a very low dissipation flow. And then you can just, you see, and transfer the spin angular momentum. This is the situation. Now, okay, so that's why then there is a significant difference between the charge current and also spin current. Spin current, there is a spin diffusion length. As I said, and this is not conserved because typically spin current is a diffusive current, which flows and then at a certain distance, which disappears. So that is a very big difference between the charge. Charge is a conserved quantity, therefore it doesn't disappear. Therefore you can make circuit, it's coming back to the end. Right? Okay, this is a big difference. And I'd like to also remind you of this continuity equation. So this is exactly expressing this conservation of the charge. But in the case of spin current, if you write the equivalent continuity equation, and this right-hand side is not zero. So that means what it is. You see, we can just rewrite this one as a kind of dynamics of magnetization, and then the spin current is generated. There is a dissipation, it's a loss. This is the pure spin current. Spin current is a kind of loss. We are studying about how to benefit from the loss. So this is a kind of spin current physics. Okay, now then I'd like to just try to relate this kind of view to the GMR, spin torque. So then, as you know, this bar magnet attracts nails, this iron. And if you look at inside, and typically this consists of this kind of magnetic domain structures. Now we just look at this boundary, which is called domain wall. Maybe all of you on this side know everything about this thing. And typically, the width of the wall is about 10 to 100 nanometers. So that's why then if you just make this, the substance in the range of this length scale, then you can combine the domain wall at will. So for example, like this, by controlling the aspect ratio, and you can just stabilize this kind of, you see, wiring or vortex type of structures in it. Even if you make this kind of junction, and you can stabilize anti-vortex structure. So this is a kind of relation. And then simply speaking, if you make the system ferromagnet smaller and smaller, and then you can stabilize the single domain structure. This is true, and then by making this experiment demonstration also shows if you go below 500 nanometers or so, and then you can stabilize the single domain structure. So this is a domain structure physics. And then now we are much more concerned with what will happen when the current flows across this domain wall. See, and then this electron carries a spin, as I said, then which is also feeling internal field, which is exactly this exchange interaction. The exchange field aligns conduction electron spins along the localized spins. That's why the electron, if this is a very broad domain wall, and then the electron doesn't feel it, and then it's just traversing, and then it's the first one it's down, but then it's the end up with up. So this is there is no dissipation or no scattering, but that is the case. So this important thing is this exchange field aligns the conduction electron spins. This is also basis. Okay, in 70s, there are lots of studies about this reflection or this domain wall resistance. So then it's a very important thing. This is a transmission probability, which is proportional to exponent of minus delta. This is the domain wall width, and this is film wavelength. In the case of metal, it is very, very thin, small, like order of few angstrom. So that's why normally this condition is the domain wall is much bigger substance. Therefore, electron doesn't peel. As I said, and it's just end up without scattering, and then it goes through. So that's why the resistivity doesn't change. But if you can somehow make atomically narrow this kind of domain wall equivalent situation, then you can see this kind of bouncing behavior. This is the origin of the giant magnetoresistance. You can realize this kind of situation by using this three tri-layered structure. So typically, then you put cobalt, something copper, and cobalt, or something like this. So this is a case. It's very similar to this domain wall scattering. Okay, so then equivalent equation or very phenomenological expression is like this. As you know, that this beta is a kind of anisotropic scattering coefficient, which you can find in the papers, and which was presented by Albert Feld also in 80s. So based on this idea, they got a Nobel Prize in 2007, and Albert Feld is very famous for these multi-layers, and also Peter Grunberg, he also did this kind of tri-layered structure. And what I learned when I knew this event, because Peter Grunberg, he was teaching, and he was not that interested in the magnetoresistance. He was much more concerned with the spin waves, how spin waves propagate in this layered structure. But he was teaching magnetic sensors to the undergrad students, and then he knew this big change is very important. And then immediately he filed the patent. So this is a very good thing, but Albert is much more pure scientist, and he is still active and working on all the very interesting physics. Okay, then I'd like to tell you the angular momentum conservation. If you go to the Science Museum, typically you see this kind of demonstration. So girl is holding wheel and then rotating, and this is regarded as a wheel is like a spin. It's somehow connected to this. There is two spins. This body is rotating. This is a localized spin. Let's say this is conduction electron spin. See, and then I'll show you again. So then you can just flip spin towards down, and then this rotation changes. So this is exactly the conservation of spin angular momentum. So this is happening when you pass the current across the domain wall. This electron is rotating due to the exchange coupled, you see, coupling with the localized spin, and then this rotate. As I said, the resistivity doesn't change. However, spin angular momentum changes because on this top changes the direction. So that's this drags the domain wall. So this is the kind of basis of the spin transfer torque or current-driven domain wall. So in 2006, and we have demonstrated, you see the pinned domain wall here. This is a vortex type domain wall. And then it suddenly moves. So this is exactly the same principle which we succeeded in observing in collaboration with a very specialist electron holography. Okay, so based on this type of idea, I think Stuart Parkin proposed this racetrack memory. Significant difference between the magnetic field and also current-driven domain wall is domain wall can be shifted towards one direction with keeping the size like this. But in the case of field, you can change directly the volume of the domain. So up this red domain is pointing on toward the right, and which is diminishing, and then it's extinguished at certain magnetic field as a function of time. So that is happening. But in this case, current-driven dynamics is completely different. That is a very big difference. And then this one is occurring due to this spin transfer torque. So based on this, and there are lots of developments, and now coming to the racetrack memory, I think Stuart Perkin is still working on this study in now Halle Max Planck Institute. Okay, now then I'd like to just get into the main topic, the spin conversion. In spin conversion, there are two very important behaviors, effects. One is spin pumping. Spin pumping is if you have bilayers consisting of ferromagnet and non-magnet, or typically platinum. And then you introduce a microwave to excite precessional motion. Precessional motion always which accompany with the dissipation. You see, this is called damping torque, which drives the spin current towards a diffusive spin current towards an adjacent layer, isotropically. And if you have this, and then the spin injection takes place, and then this has to be exchange coupled between the two. This is very essentially important because magnetization dynamics has to be transferred to the conduction electron systems. Another important is if you put here this platinum, which is a known material as a spin hole, which shows a spin Hall effect. You see, and a spin current is injected, in this case, which can be converted orthogonally flowing charge current, and vice versa. This is direct spin Hall effect, and you pass the electric current, and then spin is diffracted according to the direction of spin. Up spin is diffracted towards this direction, but down spin is opposite direction. This is called spin Hall effect. It looks like a Hall effect, that's why named after Hall. Then this is spin Hall angle, which is a kind of figure of merit, how much spin current you can extract from charge current. The ratio between the spin current density divided by charge current density. So this is an important figure of merit to evaluate materials function. So now I'd like to just show you this again, coming back to the spin conversion. Spin conversion, as I said, which is the interconvert. This, for example, like vibration, heat, and sound, which is agitation. You see? Because the spin is coupled with lattice, and then which agitate typically this kind of magnetization dynamics spin waves. And these spin waves can be, again, like a spin pumping. And this angular momentum can be transferred to the conduction electron systems, which drives a pure spin current. Now then, if you have spin-orbit interaction in your solid, what will happen is, coming back, you see the pure spin current reconverted back to the charge current. This is called inverse spin Hall effect. So this, by using this route, and then we can just convert heat or this agitation to the electricity, and vice versa. Heat mediated by this magnetic system, and then coming back to the heat. So this is called the spin Seebeck, and this reverse effect is called spin Peltier effect. And this kind of, it's a very interesting and evolving field at the moment in spintronics. So then if you know that the phonons and photons and also magnons and spins, electrons, all these quasi-particles are involved in this conversion behavior. I'd like to just mention most important conversion is a spin to charge and a charge to spin, because this is only the way to make all these behaviors observable. That means we have only the technique electrically detecting, then we can control. So this is very important. So far, this procedure was performed by using, as I said, in the spin Hall effect. It's a bulk effect. But now there are lots of new trends, and also there are lots of issues which we have to solve. This is actually the scheme which we are just working as a project. And sorry, Justin, I'm coming back to these objectives now. And then our objective is finding novel interconversion processes mediated by spins, apart from all this heat and things, light and all the other conversion process. And also, as I said, spin current is diffusive, it's not conserved. That's why if we can find some nonlinear spin conversion process, this is very, very beneficial. And then we can just increase, or we can just play with the response. And also, then as I showed, there are lots of quasar particles involved, and try to understand more fundamentally what is happening, and also how to describe the interconversion, experimentally as well as theoretically. That is our project. Okay, so far, then we have, not only my group, in our project, and we succeeded in Tohoku University, they demonstrated even this flow of liquid metal, and then there are kind of vortices, because velocity changes. As you know, the boundary condition of this kind of flow, liquid flow, at the edge, velocity is 0, but at center, velocity is maximized. If you look at, there are kind of vortex type of whirling flow, and which carries angular momentum. So this angular momentum can be transferred to, because this is a liquid metal, and the electrons spin. So, and also this distribution drives spin current orthogonal to the flow. And if you use this one as heavy metal like mercury, and you can expect spin current, therefore this spin current is converted to the charge current flowing along the flow of this liquid metal. This is what demonstrated by this Tohoku University group. And if you're interested in, please visit this Nature Physics paper in 2015. This is a very, very tiny effect at the moment, but still, as a physics, and it's probably interesting behavior is taking place in this liquid flow. And also then we have also demonstrated, and we worked on superconductor. And then quasar particle also, and it always, and when I mentioned the kind of spin Hall effect in superconductor, and the quasar particle carries a spin. Then you have to have a Cooper pair. That means there is no non-dissipative probe. And it's a spin singlet in the case of ordinary superconductor. But this one is quasar particle which exists with a Cooper pair, and which has a lifetime. It's a quasar particle. So that's why we can just transfer the spin information into the quasar particle, and exactly the same principle, and we can expect spin Hall effect. Big difference is resistivity changes completely differently in the case of superconductor, just simply because of the presence of gap at around below Tc. This just influences the resistivity so that the lifetime changes, and we can see the drastic increase in the response. And then particularly in our experiment, below Tc, then we see there's something like a factor of 2000 increase the voltage signal. But please remember, this is nothing to do with real number of electrons concerned is not increasing. Just the lifetime changes, and then it looks like a big change, amplification, but it's not really amplification. That's what we found afterwards. But anyway, this kind of nonlinear behavior, and we are studying, and also this interesting conversion procedure. So, as I said, until recently, the bulk behavior was a major thing. And now, more new functionalities can be found, either this topologically insulated surface state, and also Rushwa interface. If you have any kind of material which has inversion, broken inversion symmetry, like surface, this spatial inversion is broken. That type of space, and we can expect some special electric field exists on the surface, and which split this, this spin degenerated state in the K space, so that we have this Rushwa interface, which is Rushwa splitting. And also, topological insulator has a very, very peculiar electronic distribution, like this. So then in principle, then if you just benefit from this electronic structure, you can get nearly 100% of conversion. All the electron diffracted to orthogonally. So and then the spin can be can be detected. And also, more recently, there is a new material which is called Wilson metal, which also have very, very peculiar electronic structure. It looks like this Dirac cone, but this degenerated state is split into two due to the spin-orbit interaction, and then which produces huge Berry phase or fictitious field. So that is very interesting, and if I have enough time, and I'd like to talk a little bit about it. Okay, so this is the surface type of topological insulator, typically bismuth selenide, bismuth antimony telluride, selenium, and also bismuth antimony telluride, all this BS, BSTS, or BST. And all this material shows this surface state, and like this, and then you can see the spin current or spin up and down, flowing oppositely. This kind of three-dimensional surface state exists in this material. And then, as I mentioned, in the case of Rashba, and then if you have surface of gold, silver, bismuth, and all this silver bismuth interface, and also silver antimony, all these things are well-known combination of Rashba interface. So the common feature of this type of system is called spin momentum locking. So in the case of surface state, if you look at, this is a K-space, and always the electron flowing in this direction is locked to this spin is locked orthogonally in downwards. But then if you look at the opposite side and then upspin. So this kind of situation, which is called conduction electron spin, is chiral ordered. And in this case, in this Rashba system as well, concentric, these two film surfaces, which has chiral order, and then this rotation direction is opposite, inside, and outside is like this, clockwise, and inside and counterclockwise. This also then we can benefit for the spin conversion, and which is actually called Edelstein effect. Again, I'll show you this exactly the same type of thing, and more simply mathematically, and Hamiltonian and Dirac equations, Hamiltonian, is something like this. This is responsible for the spin momentum locking, and Z cross K. Z is perpendicular to this plane, and also K. This cross term determines the direction of effective field which is exerting on the spin system. So that's why this Z cross K gives somehow this type along this axis, the field, which is orthogonal to the propagation direction of electron. So that's this is a state, and also this similarly Rashba Hamiltonian as well, which is described with using this simple equation. Again, there is a cross function, cross term, K cross Z, which determines the effective field direction. Right? And now we apply electric field. What will happen is, as you know, the Drude model, and this film surface shifted towards one direction, so that you can have a different population of downspins and upspins. So this is, what will happen is, this is exactly the non-equilibrium spin accumulation. When you pass the current, the spin accumulates along all the surface. Then, what if you have some metals sitting right on top, and this spin could be, you see, diffusively penetrate into the adjacent metal. This is a kind of diffusive spin current. People are just believing this works. And this is, again, and these are kind of, you see, again, important thing is a figure of merit. How efficient this is described by this, which is called, in the case of direct Edelstein effect, we use a Q, this value, and which is given by three-dimensionally flowing spin current divided by two-dimensional charge current. Therefore, surprisingly or interestingly, always there is a dimension 1 over length. So this is and then this current generated spin current is somehow, in this case, in the case of topological insulator, it's 1 over BF, film velocity, times relaxation time. And then equally, and Q, this figure of merit is also given by this relationship. If you, very simple calculation, and you can work out. And in this case, this current is proportional to the alpha, which is the measure of the strength of spin splitting in the Rashba interface. But you see, and then this one doesn't look like this one, but alpha is always proportional to the film velocity. And then by considering that, then if you put this relationship in this equation, and you end up with 1 over bf tau. So it's exactly the same expression can be deduced for both cases. So the reversely, in the inverse process is like this. Now we just inject pure spin current into this surface state or interface state. And what will happen again, similarly, you see the film population is shifted, but in this case it is oppositely shifted because you inject the downspins and then this inner circle shifts towards the left, but the outer circle shifts towards the right. And the difference gives you the amount of charge current which is driven by the spin injection. So this is a spin to charge conversion by using the surface and also interface states. Again, I can show you this. This is proportional to the film velocity times relaxation time. But the relaxation time is within this two-dimensional conductive layer. And in this case as well, lambda is given by alpha times relaxation time divided by h bar. But as I said, alpha is proportional to the film velocity, and then we end up with exactly the same relationship. So this is important figure of merit, which is frequently used by when you do the spin pumping experiment with this surface state. So as I said, this bulk is shifted towards this surface and also interface. This interface state it possibly showed 100%. Okay, then I'd like to just go to this topological interface. And since 2014, based on the mechanism which I described, and there are so many demonstrations. You see like this, and I try to measure the spin accumulation by using the ferromagnetic electrode, and also by using combining with ferromagnetic topological insulator, which is doped with typically chromium or something. And then you can just study the spin orbit torque, and also this spin transfer torque STFMR method, which will come later again, and which also demonstrated by the Cornell group. But the funny thing is, they have been reporting a huge value of spin Hall angle. Like this one is, excuse me. Yeah, this one is something like 114,000%. And this is unbelievably large. And there are lots of problem discussions. This is not true. And also there is other contribution to explain this huge value. And in this case as well, then the funny thing is 100 or 150%. And this is much larger. More recently, there are also similar type of demonstration by using a spin pumping and also this direct spin accumulation measurement. And also, more interestingly, this alpha tin is a new type of material which has been found as a topological insulator, and then which was demonstrated 2 years ago by Professor Feld's group in Thalys in France. Okay, and then again, I'll show you repeatedly important figure of merit. If you do the spin pumping, which is lambda, which is given by two-dimensional charge current flowing at the interface, divided by the perpendicularly flowing three-dimensional spin current. So that's why which has a dimension unit of meter. And then this one is again the figure of merit when you use spin transfer torque, spin FMR type of experiment, which is associated with the Dirac effect. Passing current and get the spin accumulation. And this one is a spin injection and then get the charge current. This figure of merit in an opposite unit. But in order to compare with the bulk value, then you have to take this interface thickness. This is the effective thickness. Normally, this thickness is quite close to zero. But, for example, a topological insulator or any kind of interface, then you have to take into account certain crystallographic lengths, typically the lattice constant or something. and which gives 1 nanometer also, even that type of value. That's why which gives reasonable value as a bulk comparable spin Hall angle. In the case of Q, or in the case of it's a bulk, if you know the bulk material, and in order to compare with this interface effect, you have to take into account the spin diffusion length, which will be equivalent to this interface thickness, and then by multiplying or dividing, and you can get effective value, which can be compared with interface experiment. Okay, in our experiment, we just chose this BST, and BST is a typical material which has always the same Dirac cone. The slope is always same, whatever the concentration is. What you can change the concentration is the chemical doping, and then you can just vary the film level and also the carrier density. So that then you can play with just varying the position of film level, and then you can study what will happen in this conversion. That's what we demonstrated in this way. And then we employed this STFMR, spin torque ferromagnetic resonance, exactly the same kind of method which was performed by Cornell group. But in the case of Cornell group, this ferromagnet directly in contact with the surface state. The problem is that if this is coupled, the exchange coupled with the surface states typically broken, and also the gap opens, and then sometimes the electronic structure is different from the original. So that's why then we decided to introduce copper in between, and in order to cut the direct exchange coupling between the surface state and the ferromagnet. And also there's a current flows, the center of charge current, RF current, is sitting inside copper, therefore then we can apply more homogeneous RF field in the ferromagnet layer. And then what will happen is RF current excites this precessional motion. There are two torques contribution. One is a field-like torque given by this blue, and which drives the precessional motion. And then there is another torque, which is, you see, anti-damping torque. And damping is gradually this precession going to the magnetic field direction. But by this torque, which just sustain or compensate to damping. So that's why then this is called anti-damping torque. Then if you just measure by applying at the angle of 45 degrees, and what you measure is a rectified AMR signal, and then typically this red open circles is a kind of rotator, an anti-Lorentzian type of signal. And you analyze spectrum analysis will give you the symmetric contribution and also anti-symmetric contribution, green and blue. And from this, then you can evaluate the spin current information. And typically, the sign of this symmetric component will give you the spin polarization direction. Amplitude of it is magnitude of spin current. So that if you just calculate the ratio of the torque, which is exactly the same as the value, figure of merit, which I mentioned, Q, which has a dimension of 1 over length. In this case, 1 over nanometer. Then we calculated as a function of this concentration. So that means we know the Fermi level changing from this is Fermi level is touching to the bulk conduction state, but then gradually on inside gap, here, the surface state appears, and it's Q almost constant, but then when you achieve the Dirac point, and then going down, and then coming back again, and then this open square is already this Fermi level is touching to the valence band. So that's why then it's no more reliable, and there are different contributions. Okay, and then as I said, this effective interface thickness. We took 1 nanometer, which is called a quintuple layer thickness, and which gives 52%, which is much larger than the traditional metal values, such as tantalum, beta tantalum, or tungsten. So this is the one. And also, by making chromium doped BST, it's right on top of this bismuth BSD system, topological insulator, you can play with the spin-orbit torque. Maybe some of you are working on the spin-orbit torque. So this one, you see the surface state create spin current coming up, you see, the perpendicular to this interface. And then if typically this chromium doped magnetization is perpendicular to the surface, and which fields a spin-orbit torque, which drives magnetization moving this direction. And also, if you apply magnetic field orthogonal, so this is the origin of spin-orbit torque, and which is driven by the spin current generated by the spin accumulation at the surface. And a very interesting thing is, in this method, obtained threshold current is much smaller than which is realized in the metallic system, with typically this platinum and cobalt batteries. And in this case, you see order of magnitude smaller. That's what we observed. And then you can just switch back and forth. This kind of preparation of sample is very difficult. And this is a PhD course students who work with Professor Tokura, and he worked very hard and realized and succeeded in this type of experiments. And based on this, he can also memory effect, like by applying a pulse, and you can change the magnetization direction either up or down systematically. So that was the demonstration. However, I'd like to just stress, this is only, you see, demonstrated at 2K. It's very low temperature. Otherwise, this ferromagnetism disappears. Curie temperature is very small, low. But more recently, there are two demonstrations. One is, I think, this one, or this one, I can't remember. But the one is Singapore, National University of Singapore group, Professor Hyun So Young's group. And also this one is, I can't remember, but by using bismuth selenide, this one has also bismuth selenide, and then they can just demonstrate magnetization switching due to the spin-orbit torque at room temperature. This is also the current necessary for the switching is very small. Okay, now then I'd like to just switch my talk to the Rashba interface. Okay, and as I said, the Rashba interface is very attractive for this conversion behavior. And initially, then it was well known from the ARPES, angular resolved photoemission spectroscopy measurement, that this, you see, any kind of surface, gold, silver, and bismuth, and which shows a spin splitting like this. And particularly in the case of bismuth silver 111 surface alloy, which shows huge energy splitting here, then it amounts to something like 200 millielectron volt, which is much, much larger than the others. So that's why that means that you have definitely the spin momentum locking in this interface. And based on this idea, Professor Alfred Feld's group and then this researcher Rojas Sanchez, he demonstrated all this interface effect. Permalloy silver, permalloy bismuth, permalloy, and then with interface. And then only the case with interface of silver and bismuth, they see this huge rectification effect due to this spin by using a spin pumping method. So this is a kind of first demonstration. Since then, there are lots of demonstrations, including our study. We also then thought this is very interesting, and we wanted to, for example, if you just make the metal oxide or insulator interface, then we can play with the gating. So that's the one of the kind of aim. And then we prepared copper and bismuth oxide, and then there is the ferromagnet sitting underneath in this case. As I said, in the spin pumping, drive the spin current towards the interface, and if you hit the resonance condition of this permalloy, then you see this huge increase. That means spin to charge conversion takes place when you just inject by spin pumping method. So this is kind of interesting, and then if you're interested in, there are some two papers. And also then we try to understand what is happening at the interface, and we just vary the materials like silver, gold, aluminium, and copper. And a very interesting thing is silver and copper, which shows opposite sign, and the magnitude is quite large. Now, then it's just we plotted the absolute value of this alpha, which can be deduced from the experiment, like this. And then this axis is the difference between the two work function of the two materials. And the difference is becoming smaller. That means work function difference is smaller and the Fermi level is closer. And then this effect is increasing. And in collaboration with theorists, they did the first principle calculation, and this tendency is exactly reproduced. And we can now understand this splitting strength, alpha, which is given by the product of this asymmetric Coulomb term. This is the slope of the potential across the thickness, across the interface. And this one is a kind of interface state wave function square. That means charge density, which are existing along the interface. Interesting thing is, and if you look at copper and also silver, you see this one, this purple curve is electron distribution, charge distribution. Charge distribution is increased near the interface, and then this is a case, both cases, that's why, which contributes a lot to increase this alpha for copper and silver. What determines the sign is this potential gradient, this term, and this is a potential gradient. And if you look at on the copper, in this region, very close to the interface, always in this positive slope is a majority. In contrast, in the case of silver, here the negative slope is majority. Therefore, this we can understand somehow quantitatively that the sign change takes place from this first principle calculation. Okay, and also there is a kind of demonstration by using oxide-oxide interface. As you may know, this LAO and also STO, which form the two-dimensional gas in between this insulator. And then you can also then expect this similar type of Rashba interface. And if you do the spin pumping, and in addition to that, then you can do the gating. And then this French group shows a huge spin charge conversion, and also then which changes as a function of gate. And this is actually lambda, the figure of merit, which I mentioned previously, which changes from 2 minus 6. And if you change the magnetization direction, with minus 2 to 6, you see, as I said, the big value so far obtained is something like 2 nanometer or so. So that's why then this is gigantic. And then you can really modulate this spin conversion. This is very surprising results. So then I'd like to just compare all these interfaces and metal interfaces, typically around something like 0.1 to 0.4. This is a big value. We're using this is very famous Rashba interface. And in our experiment, it's also more or less the same as this metallic system. And this insulator oxide-oxide interface, and which shows a very large value. This is very interesting. But you have to remember that the carrier density is also very important. And you cannot flow so much current in the case of this interface two-dimensional gas system. So now I'd like to just show that there are still various spin splitting in different symmetry. For example, polar type of, even the crystal bulk system also shows this kind of Rashba, and also Dressel-Haas type. And also then if you have the chiral system, then you can expect wild type. That means if you pass a current in this direction, spin aligns to the current direction, and also they oppositely aligned or something like this. So then that means you can expect different functionality. Right? So this is a kind of motivation to work on the different materials. Particularly, I'd like to just mention this recently, the manganese this X system. This is a non-collinear antiferromagnet, and which is drawing attention of a lot of researchers, particularly this Stuart Parkin and all the Claudia Fels and the Max Planck Institute people. They are working. Actually, we are competing with them. But a very important thing is, which I'd like to mention here, is typically, if you want to have a large response in any kind of physical property, then you use ferromagnets. Large M, large response, magnetoresistance, and also optical, magneto-optics, some electric, anomalous Nernst effect also. But the antiferromagnet, so far, we know the response is very small in many. It's because magnetization is fully compensated, it doesn't respond to the external magnetic field. But this novel antiferromagnet, this non-collinear system, which shows the very, very small magnetization, because somehow almost vanishingly small magnetization, but response in the anomalous Hall effect is gigantic. And this material, draw lots of attention why this shows such a large response. And one of the reasons is because of this peculiar electronic structure, the presence of these wire points. It's like a Dirac cone and a pair of Dirac cones. One is acting as a positive and the other one is a negative pole, and which is responsible for the fictitious field, which is exerting the field to the moving electric electrons. So this is a very important concept, and this material, therefore, attracting, drawing a lot of attention. So, then as I said, this kind of Kagome lattice and a frustrated system, and the magnetization of this manganese, typically, it just carries only the 3 millieV per manganese atom, and then empirically, anomalous Hall effect is given by this simple equation. And if you just put this value in this M, and what you can expect is a magnitude of amount to something like 0.01 sorry, this one is micron centimeter. But when you measure, and the response is huge, gigantic, and then about 3 micron centimeter. So this is, I think, the matching to the ferromagnetic value. So this is simply due to, as I explained, due to the fictitious field, which amount to something 200 Tesla, and then which is also generated by the Berry phase, in otherwise distinctive nature of wire antiferromagnet. So then there's the real space in this Kagome lattice and frustrated system, and case space, and we have this wire nodes, and this is a kind of scenario. And people trying to understand this very curvature really realizes in this system. So there was the first principle band structure calculation, which shows the one particular symmetry direction in case space. You can see this Fermi level, and you can have this so-called wire point, and which is responsible for this type of feature. That's what we can see. And now this is just calculation. And then people may ask, did you see it? Then it's in my institute, people that they tried, and then measured the Fermi surface, and also the band structure comparable to spectroscopy results. And they are now sure that this is a kind of proof that there is a wire point in this system, particularly in this Fermi surface. So, and also, I'd like to mention, there are certain activities in Claudia Fels and Stuart Parkin's group in Max Planck Institute. They observed a similar type of response in manganese-3 germanium, and also theoretically they're expecting, as I said, when current passing one direction, you can expect spin polarization along the current, and which they call spin current angle. How much current you flow and how much polarization you expect. And then if you're interested in that, there is a kind of paper and in this topic. So then we are just typically this kind of, if you see the large anomalous Hall effect, you can simply expect spin Hall effect may take place. So that's why when we did this typical standard measurement, we just use an FIB and cutting slab out, and then it's orient to the particular crystallographic direction, passing current. If there is a spin accumulation along this surface, and then if you have this, you see, putting a line, the electrode, perpendicular to the current flow. So that means these two electrodes doesn't detect any voltage change. But then if you have the ferromagnet on the one side, and then this is detecting chemical potential because it's a ferromagnet. And then we can measure the spin accumulation taking place at the surface. So that's the idea, and then we did the experiment. And so what we can expect is if there is a spin accumulation on the surface, and then the detector manifestation can be flipped back and forth. And you can expect this kind of a tiny hysteresis loop, and which corresponds to the spin accumulation. And then, as I said, there is a small staggered magnetization. We just fix this one first and then downwards by applying a large magnetic field, and then only flip the soft magnetic detector, the back and forth, and which flips very small magnetic field like this. And then the very funny thing is, when you change the staggered magnetization direction from downwards to the upwards, and this accumulation signal changes the sign. This is, if I say this, maybe because you are changing the small magnetization direction, therefore it's not surprising. But in the case of ferromagnet, you don't expect, even though when you change the magnetization direction from up to down, but spin Hall effect and spin accumulation is always the same. The reason is, okay, the spin current is time reversal even. Even though then you change everything, you see, rewind the time, spin current doesn't change. Upspin go down, and the propagation direction is opposite, and also downspin becomes up, and the direction of the propagation changes. As a result, it doesn't change. So that's why this spin Hall effect equivalent, this spin-Seebeck effect doesn't change as a function of angle or ferromagnet, but anomalous Nernst effect, which is corresponding to the anomalous Hall effect, changes the sign. This is a significant difference, which was reported by this paper, which was performed by Johns Hopkins group, headed by Professor Charlie Chen. In our group as well, this is unpublished data, but we did the similar type of experiment. We're using this non-local spin bulb method. We just generate by using copper bismuth spin Hall material. The spin current is generated and propagated and absorbed into this wire, and we change the magnetization direction by applying magnetic field on toward the right or left. But even though then you scan magnetic field back and forth, you don't see then only a stable value here. But as soon as you change the current direction, this value changes to here, this positive and negative. At the moment, we cannot explain what causes this offset, but still, this difference is always constant, whatever the current is. So that's why then we believe the spin Hall effect doesn't change the sign, although then you may change the magnetization direction. So this is a very important thing. So that's why then this is a case for ferromagnet, which doesn't change. But in our case, in this antiferromagnet, it changes the sign. This is very, very different. Then, in order to understand more, we did the angular dependence of this spin accumulation along the surface, and also this by just odd component. And then we just plotted this one as a function of angle. And also, toy model calculation was performed by our collaborator, Alan MacDonald, and also this Fa Chen. And they did their calculation shows something like this kind of variation. Our experimental results also follows very, very similarly, which convinced us we are observing the sign change in this material. It's very different. And also then we performed the spin pumping experiment, and also there was a very strange behavior. You see, for example, in the case of ordinary spin pumping experiment, this is a case for platinum. When you just positive field, it's negative, and in that case, when you just change the magnetic field towards a negative field, and then if it changes the sign. So this is what happens. If you just have this spectrum, then it's a positively spike, and then here this has to be negative if ordinary spin Hall effect is the origin. But in this case, again, that is both positive, which is exactly the case for the spin Hall angle changes its sign in our case. This is a new finding. And also then what we can just understand from this type of experiment is there are two contributions always in the solid, and also which is strongly related to the symmetry of the crystal structure and also spin. In the case of non-magnetic metal, and then according to the Alan McDonald's equation, there are two contributions in the spin density matrix, a diagonal contribution and an off-diagonal contribution. Only diagonal contribution includes the tau. This is the time, the relaxation time or something, time scale, and the electric field, which causes the change in sign. That's why when you reverse. But in the case of off-diagonal contribution, it doesn't include this tau. Therefore, when we see this very strange, in the case of spin pumping, always same sign appears. So this is, and then in summary, we can have this kind of magnetization line this direction, always spin accumulation is orthogonal, and then the current is flowing in the same direction, and also this magnetization, then the spin accumulation is again an orthogonal, which is along the current direction, and a very different type of response is expected in this type of system. Okay, now then I'd like to summarize my talk. And today, just I show you a lot of examples of topological initiator and also Rashba interface, and also as a second topic, I showed you the novel magnetic spin Hall effect in non-collinear antiferromagnetism only 3T. Okay, thank you very much for your attention.